Hello, everyone, and welcome to my talk about data-centric AI. So first, a little bit about me. My name is Marysia. I'm a data scientist and data science educator at Go Data Driven. And today I'm here to talk about something that I'm very passionate about, which is data-centric AI. Data-centric AI is the idea that in order to prove our model performance, we must focus on the data rather than the model itself. And because of that, I want to focus on two things. First of all, why is this concept of data centric AI interesting? And second of all, how you can get started actually applying it to your use cases and your problems. So let's start with an example of a typical data science project. Say because of global warming, we feel bad about the penguins and that they can't fly. So in this case, we're doing a use case where we try to build wingsuits for the penguins. But in order to build wingsuits, we need to approximate the body mass of a particular penguin. And it turns out that we don't have that data. So rather than to ask the researchers to go back into the wild and collect all that data from the penguins that we want to build wingsuits for, we decide to approximate it because we do have some other data. So we have some features, the species, the sex, the flipper length, the common length, and the common depth. And our initial approach here would be to try out a couple of algorithms. Let's say a linear regression model, an SVM, nearest neighbors. And in addition to that, we would tune the hyperparameters with a grid search. So that seems like a very reasonable approach that should get us some good results, right? Well, it turns out that our results actually aren't quite up to par yet. So it turns out that if we look at the data itself, we have some missing beak lengths, common lengths. And whereas we initially decided to drop all the data entries that had missing data, that actually ended up deleting quite a lot of data, and that wasn't the smartest approach. So we try something that we would normally do. For instance, we decide to replace these values with the average of the column. So we look up the average common length, replace the missing values with that, and it already improves our model a little bit. That's already a better, but after some careful exploratory data analysis, we actually discover that there's a correlation between the sex and the species and the flipper. So rather than simply replacing the mean, so replacing the missing values with the mean of the column, we decide to replace it with the mean of this particular species and sex of the penguin that we have at hand. And this will probably lead to much better results because the choice that we make about our data and how to replace that is a much more appropriate choice for our problem. And these are the kinds of decisions that we make every day as data scientists. We know that modeling is much more than simply tuning hyperparameters, and that the decisions that we make regarding our data can have a lot of influence on our result and our model performance. Whether that is to choose to impute by the mean or by the mean of the sex of the species, that actually has a larger effect on the eventual model performance than whether you choose to use the Gini and entropy criterion for your decision tree, for instance. The choice about your data is also has a lot of influence. It's not just about the modeling hyperparameters or the algorithms. So that's what we say, why we say that a modeling pipeline is more than just the algorithm. It's also the choices that you make in terms of data transformations. And a lot of these data transformations are made very easy. For instance, in scikit-learn, where a lot of them are pre-implemented, but not just with the missing value imputer, but also how you choose to encode your data. Do you use one-hot encoding or ordinal encoding or target encoding? Or how you scale your data, for instance, with the min-max scaler, the standard scaler, the robust scaler. So these are all choices that we make because we know that these choices influence our eventual model performance. However, in our penguins example, even though we made all these data transformations, the results were still disappointing. And it turns out that upon further inspection of the data, that one of the research interns who recorded all the penguin species measurements made a little mistake and accidentally recorded everything. So the common length, the depth, the flipper length in centimeters rather than millimeters. And that completely threw off our model. Because no matter how many hyperparameters you tweak or what data transformations you choose, if the underlying data is bad, your results are also going to be bad. Andrew Ng once said that data is food for AI, but you can do all the transformations you want to your data. If the ingredients are rotten, your meal is never going to be any good. And that's also why he said that the focus has to shift from big data to good data. Having 50 thoughtfully engineered examples could be sufficient to explain to a neural network or the algorithm what you want it to learn. And that's where the idea of data-centric AIs come in. So whereas the original modeling approach is for model-centric AI is that we have data transformations, we have our algorithm, we evaluate a model, and based on the evaluation results of a model, we might go back and change some of the transformations or change the algorithm or the hyperparameters. The idea behind data-centric AI is that you go back even further. You don't just focus on the algorithm, the hyperparameters, and the data transformations. You also focus on the underlying data. Data-centric AI allows you to iterate on the data as well, rather than just the model. But why are we so focused on data now? And why is that a new idea? Isn't that what we've always been doing? After all, this whole motto of garbage in, garbage out has always been the idea. And monitoring your data to discover errors has been standard practice for decades, and popular techniques in active learning date back to at least the 90s. So the question is, what is different now that I am here today to tell you about data-centric AI, while we always knew that data was very important and data was essential to the quality and the performance of the model? Well, think about deep learning. Deep learning itself and the algorithms underneath that weren't a new idea in 2010, 2012. The first perceptron by Rosenblatt was actually published in 1958. Backpropagation stems from 1986. And even the first convolutional neural networks were already around in the early 90s. So the ideas weren't new, but the ground has changed. For deep learning, in from 2010 onwards, we had large scale annotated data available. We had better hardware and GPUs available. And those things had a massive effect on the revival of deep learning. So while the idea itself wasn't new, the interest and the hype around deep learning certainly was, because the ground has changed. And I want to argue that that's also the case for data-centric AI. This is a term that is now coined, that there's a lot of attention about. The idea that data is important has always been around, but I think, and I would like to argue, that that idea is way more relevant now than it was, let's say, 5 or 10 years ago. And the first reason for that is unstructured data. For tabular data, we can utilize descriptive statistics, quantile statistics to better understand our data set. We can create visualizations, investigate correlations between features to get an idea of the data at hand before we start modeling. And in this case, a simple histogram of the data would have revealed there's something odd going on with the data. Some body masses are suspiciously low here. And if we got this result after some proper exploratory data analysis, this would naturally guide us to focus on the good data quality. We notice this easily, so it's easy to also do something with it. However, this is something that is remarkably more complicated when we get to unstructured data problems, like audio, text, or images. First of all, unstructured data problems are typically deep learning problems, which means they require much more data. So getting a good overview of the data at hand is more complex. And second of all, it's much more difficult to get a good insight in the data at hand with unstructured data. Sure, you can sample a few images like we've done here, but does that really tell you whether your data is good and representative? In this example, this is actually a real data set that I gathered for classifying which out of the three penguin species we have here. So there's the three penguin species, Gentoo, Chinstrap, and Adelie. And this data set was sourced by simply downloading the first few pages of Google image results. And sure, we can see that there's an odd result in there. We see that there's a report card with a very tiny picture of a penguin. But it takes a little bit more focus to see that the penguin in the middle on the left is actually not an Adelie penguin at all. It has this little chin strap around its chin, which means that that's a typical characteristic of the chin strap penguin. And this is something that we can only discover, it seems, by randomly sampling some images. And my whole data set was about 5,000 images, and these are only 9 of them. So how can we be sure that the data set isn't full of these kinds of mistakes? Because we're dealing with unstructured data now more than ever, and unstructured data is harder to explore, we are in desperate need of toolings and techniques to help us out with this. And that's also one of the things where data-centric AI comes in. And that actually brings me to my second point, the rise of foundation models. Traditionally, unstructured data used to be tackled by training a deep learning network from scratch for every single task. And this meant that if we wanted to train a model that can distinguish between a car and a truck, we had to fully devise the architecture and train all the model weights so the model could make sense of the image. Then, once it had an understanding of how the image must be processed, only then could we learn which images corresponded with trucks and which ones with cars. However, we quickly discovered that there's a lot of overlap between many of the unstructured tasks. Whether a model needs to determine the topic of a text or whether that text is positive or negative, in both cases it requires an understanding of language. And the same goes for images. Therefore, it seems silly to let every neural network learn all these generic features, how language works, what shapes you can find in an image from scratch. And that's where transfer learning comes in. Because with transfer learning, we fine tune a pre trained model to our own data in order to solve a problem. And that means that a model that was originally trained to differentiate between trucks and cars, with very little fine tuning, can actually be very easily used to determine whether something is an image of a dog or cat. And transfer learning can even happen between various tasks. A model may have initially been trained to predict the next word in a sentence, but as these models require an understanding of language, with the right data, they can very easily be tweaked to a completely different task, such as predicting whether a sentence has a positive or negative sentiment. And that's what we mean when we refer to foundation models. Foundation models are very large pre-trained models that can be used for different tasks with minimal fine-tuning. So examples include BERT, GPT-3, DALL-E, Stable Diffusion, all these models that you've been hearing a lot about in the past year or two. So foundation models are really large, and in order to perform a completely different task, they need the right examples. And it turns out that foundation models benefit much more from good data than from a lot of data. I was initially taught that simple models, especially with a lot of data, are the best at generalizing because overparameterization was a major concern. But now we have large models that actually are a counterexample to that idea. When we provide these very large models with a few good examples to fine tune on, it is almost as if we're overfitting them to our very specific problem or task. And because foundation models have become much more user-friendly and commoditized, we as data scientists simply don't have the resources to compete. When you look at GPT-3 or BERT or ResNets, the architectures of these models have an incredible number of parameters, and it is completely unfeasible for most of us to create and train those from scratch. And we typically also do not even have those huge data sets that they were trained on at our disposal. But because of transfer learning, we can still use these pre-trained models and fine-tune them on our own much smaller data sets. And that means that the competitive advantage of the data scientist lies in everything that surrounds the model. So, whereas we don't necessarily have to focus on the algorithm that much, because that is provided to us with some model weights, it makes much more sense to focus on the data because the data is unique to your use case. And improving the data can be easier and have more impact than focusing on the model. So, a question I very typically hear when I talk about this topic is, but doesn't quantity compensate for quality? Doesn't a lot of data compensate for the lack of quality of the data? If we don't have that good data, why don't we just gather more and the model will learn what is right? Because there's this persistent idea that simply gathering more data compensates for the lack of quality. And sure, that might be the case for some problems. But the problem with that, however, is that when you're gathering more data, you're gathering data in the same way, which means the same problems will persist. So, will more examples of Adelie penguins compensate for this one chin strap that got caught up in the mix? Or the paper report card over here? Sure, probably. It probably will. If you gather enough examples of true Adelies, but if you gather more data, two things happen. First of all, you're probably also gathering more bad data. And secondly, the model that this was trained on this data or trained on 10 times this amount of data will still have the same problems that the original data set has, which is, for instance, in this case, that none of the examples here that you see are of baby penguins because there are no baby penguins in the data set, and therefore the model will not be able to identify them. Therefore, we must be mindful that when we gather more data, we also gather the right data. So, what is the right data? What is good quality data? What is the kind of data that we would like to gather or have in order to solve our unstructured data problems with foundation models? Well, first of all, the labels, of course, should be correct. So, in this case, when you see a couple of examples of dogs, my dog actually, there's one picture in there that quite clearly doesn't present it. And if it has a dog, it is going to confuse the model that is learning. Second of all, data labels should be consistent. Good data is consistently labeled. This might seem obvious, but this is not always the case. And sometimes that's simply because of unclear instructions. In this case, the labelers were instructed to put a bounding box around the penguin. But does that mean one big bounding box for both penguins or for each penguin individually? And a good data set should also be representative. That means for our penguins examples, images from the front, the side, individual penguins, penguins in a group, on the ice, in the water, and on land. And yes, even a baby penguin. We have to be mindful that all the ways that we expect to use our models in practice and what kind of data we expect to occur there. And lastly, good data should be unbiased. A model trained on biased data will in itself be biased as well. In this example, a clear distinction is made between the presumed occupations based on gender, and because the model is not bad in itself, but the underlying data it was trained on was biased. And this is very often the case for language, but also for images and other forms of data. And there are many forms of bias, too many to tackle in this talk, and it's a topic too complex to do right by here today. But there are many tools out there, as I have screenshot here from the Data-Centric AI workshop at NeurIPS last year, that I strongly recommend. So the question is, how can we make steps towards this? If, let's say, you're convinced your biggest performance gain is to improve the quality of the data rather than tweak the model parameters, how do you start? Well, first of all, good quality data is correct data. That means you want to identify badly labeled data, and sure, you can manually inspect the images, but there must be a better way, right? One such way is to use a model to get predictions. This can be an existing pre-trained model. For instance, any model trained on ImageNet will probably have the label dog. Or alternatively, you can fine-tune a pre-trained model on your initial data. And once fine-tuned, you can pass the data through the model and look for the discrepancies between the predictions and the ground truth labels that you have. The model doesn't need to be perfectly tuned to your data set. It just serves as a guide to what might require your attention, especially if you sort these predictions by confidence of the model. It should quickly draw your attention to the mislabeled data points. But even without labels, existing pre-trained models can serve as a guide where to focus your attention. Because when data is passed through a network, whether that's text, image, or image data, it goes through two stages. The body of the model, which encodes the input data in some kind of numeric format that represents the image or the sentence and its features. And then the head of the task, where the encoded version of the data is transformed into a prediction. The result of passing data through the body of the model before it gets converted to a prediction is what we call the embedding. And the embedding is therefore a numerical representation of the input. And embeddings can be very useful to determine which inputs are similar to each other and which ones aren't. For example, we can visualize them with the dimensionality reduction techniques like UMAP. And in this case, our attention is immediately drawn through to the orange, the dog, right in the middle of a bunch of cats. And because this was plotted with the interactive Altair library, that means that when we hover over the data point with our mouse, we see that it in fact represents a cat. So this was mislabeled. Is this something that you always have to do manually? No, because of the increasing interest in data-centric AI, there are a lot of tools out there that can help you do these kinds of things and become increasingly available. One of these tools is the out-of-distribution detection from CleanLab, because with just a few lines of code, you can find samples in your dataset that look strange or different from the majority of samples in your dataset, either based on a classifier or their embedding. In this case, the training data was a subset of CFAR10, only the animal images, and the top outliers that this code identified amongst the test set data were all non-animal images, as you can see. And this approach is based on calculating the distances between the embeddings, and data points with an above average distance to their nearest neighbors are considered out of distribution. CleanLab even advertises that they can fix all of your label issues out of the box by automatically finding and fixing errors in any ML dataset. A second thing, however, is that you want to maybe identify ambiguous data points. Another challenge, for instance, this one, where the label was dog, but would a model really be so wrong if it thought it was a cat? This is also somewhere where you can use a model or the embeddings. In this case, by using two models, each model was trained in such a way that it picks up slightly different things, maybe because the architecture was different or the data that it was trained on was different. And again, it's the discrepancies that you're interested in. So if one model thinks this is a dog, the other model thinks this is a cat, that is an interesting data point for us to manually investigate. Or we could look at one single model and simply look at the decision boundary. Images, in this case, that the model was less certain about. Is it a dog? Is it a cat? Those are more interesting for us. So then it is up to you to decide what you want to do with these data points. Maybe you want to get rid of it because it's a bad example. Maybe you want to put it in your validation set. The choice that you make is up to you, but tools like this help you identify the interesting data points. And that brings me to my next point. It's also important to carefully craft your train and test split. So for structured data, that's very easy with scikit-learn, but for unstructured data, it's important to carefully craft your train and test split because the distribution of your train and your test set have to be similar. So one of the ways to do that is through profiling your data. That is easy for tabular data like pandas profiling, but it's also something that you can do for your image data, for example, with a tool like ylogs, which is a open source data logging library. In this case, you see information about the images in your dataset, and for instance, you can see the distribution of the blueness of your validation set versus your training set, which can lead you to believe that there are more images of penguins in the water, for instance, in the validation set compared to the training set. But again, I like to focus here on the embeddings because that tells you a little bit more about the content of your data because they're a representation of the numeric input. Yeah, so by retrieving the embeddings and plotting them and comparing your training set to your validation set, you can see, for instance, in this example, the validation set was missing quite a lot of the stuff on the left here. And my advice would be to focus on the validation set quality. Make sure that your validation set is complete and representative. It doesn't matter how much you tweak the model or the data. If your validation set is bad, you won't see the difference. So make sure that your most difficult examples for your model are in your validation set and not the easiest ones. And that brings me to my last point. Make it easy to iterate on your data. Whatever you do, make sure that it's easy to version your data and change your data. And that can be through low-tech tools, as you see here in an example where we simply use Google Sheets and a bunch of images to relabel. But that could also be with high-tech tools like data version control or building pipelines that allows you to easily relabel images. It doesn't matter which tools you use, whether that's high-tech or low-tech, as long as it's not a burden to make quick changes to your data. So, in summary, how to get started: identify incorrect and ambiguous data points and labels. Focus on carefully crafting your train and validation set. Make sure that they're representative of your real problem and focus on the quality of your validation set above anything else. And lastly, make it easy for yourself to iterate on your data sets. Version your data, easily relabel your data, whether that's with low-tech tools or with high-tech tools, but don't let that be a burden. And in summary, don't treat your data sets as static. So that was my talk. I hope you enjoyed it. Feel free to reach out if you want. These are my details. And back to you, I would say.
Hey, Marysia, I think we've got about like 2 or 3 minutes left, and we can select a question to answer. I just like pinned to the stream as the question described. Was there any like tools you could be like recommending to people who are looking forward into this idea?
Yeah. So the problem with this is we like to focus on creating more tools to make things easier for us, but at the same time, the whole the whole idea is that your use case is unique. So it might not be the case that a tool that I like to use is also good for your use case. There are a lot of really good resources out there. There's the Y-Data, awesome data-centric AI list of all kinds of tools. And there's one by Hazy Research that I can also recommend. It just gives a list of all these different, for instance, labeling tools for different types of data, and you kind of have to mix and match what works best for you. I would simply advise you to look what works good for you, and to keep a lot of the control with yourself. So, for instance, I really like that CleanLab has this out of distribution detection, and I use that. But I don't really like to use the whole fix all the errors in one go pipeline because I don't know what's happening then and what's happening to my data. And I lose a bit of control there. So I personally like to look for the tools that do the specific thing that I want, but not one thing that does everything in one go. But again, Y-Data and Hazy Research have a really good list of tools out there that provide a good start.
All right. I think that will be all. And thank you for coming. That was a great talk, by the way.
All right.
And
Thank you for
next,
having me.